So, where do you want to start? Exam number 1 covered a little bit of review of intro stats. There were some of those kind of questions on there. And then the basics of simple linear regression. We hadn't done any multiple regression at that point.
That's where we did the confidence bands and the prediction bands.
Uh-huh. Yes, and so...
And you can only do those with simple linear regression, right? When you do... Like on the SAS, I guess. You know how they would make that pretty graph?
Oh, yeah. Yeah, no, you can do it in a multiple regression. You can get a graph where you get a fit plot, they call it, with bands on it. But I don't know that SAS will produce it for you, but you could produce it. But you have to pick, okay, which x variable is going to be my x-axis here. If you've got 5 x variables in your model, then you can't do a 6-dimensional figure and put those bands. But theoretically, there's no problem with that. And you end up with a sort of a ellipsoid kind of thing with a confidence ellipsoid around it kind of thing. But you'd have to pick an x variable and do the plot for that x variable. So, yep.
The F statistic is the T statistic squared, correct?
In a simple linear regression, that's right. So F is equal a T squared, and let's say T with degrees of freedom, whatever it is equal to an F with 1 degree of freedom in the numerator and degrees of freedom in the denominator. Right? So only if your overall model F test is in a simple regression will that numerator degree of freedom be 1. So that's the only time it works. But what's that?
I'm trying to access that and have test 1, so I'm just trying to pull this all in.
Yeah, what you're seeing here is some of the old intro statistics review. Or actually, it's probably more like 344 or 343 review, but what does this expression mean? Epsilon sub I tilde. Okay. The residuals are independent, identically distributed, normal, with mean 0 and variance sigma squared epsilon. And the important thing about this sigma squared epsilon is what? Notice this has a subscript of I on it.
That first statement is the errors at each I.
Right. And this doesn't have any subscript of I. So it's saying it's constant. All of the residuals have that same. There's no subscript there that depends on which part of the data you're in. Right. Yeah. Independent and identically distributed. There's some residual plots to look at and determine if you think all of the assumptions are met. Look at what?
This one that has like the... maybe that's test 2. I think it's test 2. Never mind. It's this.
Okay.
Yeah, which has the crazy plane thing.
Oh, yeah. Yeah. So probably the hardest thing on this test is knowing the formulas to do standard errors for slope and intercept, standard error of a mean predicted value, standard error of an individual predicted value, and then do the confidence interval for predicted value and prediction interval for an individual. If you look at problem G on the 3rd page, this one. It says estimate the systolic blood pressure for an individual with a QET value of 4. Compute the 95% prediction interval. What's the formula for prediction interval? Yep. So you need SE. And what is SE? That's root MSE. It's the standard error of the residuals, right? Or it's the variability in the residuals, right? So that's root MSE. So then standard error of Y hat individual. I don't have a slick way to write that because it's Y hat whether it's a mean predicted value or an individual predicted value. So I just write IND for individual. So standard error of a Y hat for an individual is this SE and then times
X bar minus X.
okay, XI minus X bar squared over
Minus 1 and X squared.
Yep. Okay, good. All right, so which term in this causes it to flare?
The last one.
This last one. Because you have a factor in here for how far away from the middle of the x's it is. And the further away it is, the bigger this term gets. So standard error gets bigger. Right? What does the confidence interval for a mean predicted value, how does it compare to this one? What's different? Take out the 1. And remember that 1 is there because the rest of it is to predict the mean, right? So it's the confidence interval for where the mean is. And then say, okay, well now I got to figure out, well, how far would an individual be away from that mean? That's a whole nother residual variability, right? So you add a 1 in there so that when you distribute this in, you get an SE squared there. Okay, we had a proof on this test, this one. Any questions about that one? I think I went through this one when we did that test, and you probably wrote it down, so you may not have questions, but anybody? Okay. So off of this first exam, I would definitely be prepared to do this kind of thing. Filling in an ANOVA table, I probably won't have one of those for a simple regression. It'll probably be a multiple regression one where you have to fill it in because it's all kind of the same stuff. The bottom line here of where it says QET for the one variable in the model, filling those in is kind of a lot of this stuff. So that, I might not have you fill a whole table in, but I would probably ask you about that. Getting the confidence limits for a slope parameter works better in a simple linear regression model than it does in a multiple regression model. So that's where I would ask those kind of questions. Remember what you have to do in a multiple regression model to get the confidence interval for the slope of a particular variable? Yeah, you got to use that hat matrix thing and the x prime x inverse matrix, and it gets really annoying. It requires me to have a lot of SAS output on the page for you to sift through and find.
Save yourself.
Yeah, save myself that trouble.
Do it for you.
Okay, so then exam number 2. I probably won't spend a lot of time on anything matrix related, but a little bit just to make sure you know the matrix equations and how matrices get used to solve for things. But I probably won't have you do any solving of matrices like I did here, but then on this first page, if I scroll down, is the one that you were asking about, Taylor, right?
Yeah.
That one?
It's interpreting the negative.
Yeah. So I don't know if that's really showing up or not. Let me put this up, and I'm going to scroll it down a little bit lower. What you'll hear this referred to sometimes is a response surface. So this is corn yield per fertilizer. So we have amount of fertilizer used in pounds per acre of 2 chemicals. So this is P2O5. Does anybody know what that is? It's a... I don't know, so don't expect it. I'm a statistician.
I took chemistry, but I hated that part.
Yeah. And this one's K2O. So K is potassium. So I know potassium is one of the main fertilizers, and this is a phosphate of some kind. So phosphorus, basically, right?
Do you mind if I try and find it on?
You don't. It's not important.
Okay.
Right. So phosphorus, potassium. How much of each? What's the optimum amount to use? But the question that it says, suggest a model to fit this data, and write out that model using Greek letters. So what do you notice about the shape? Okay. If you look only at the phosphorus levels, right? As you increase phosphorus, this is increase. This is the 0 down here. It's kind of backwards from what we're used to. So this is 0, 0. So as you increase phosphorus, you get a big increase in yield, and then it starts to tail off, right? Or if you go to one of the other levels of potassium, you get basically the same shape, right? So what kind of model would you suggest to fit that, ignoring the other variable? Yeah, it looks quadratic. It actually doesn't look that much quadratic. It's got a weird shape to it. It's not a parabola, but a quadratic would probably fit it fairly well. Right. Then if you go in the other direction, just looking at that, right? And part of why this is funny is because you don't have an intermediate value in here. This is probably going to tail off. And so the nature of the data anchors it here at 0, 0. But corn yield, what happens if you don't put anything down? You still get some corn. It doesn't go to 0. So that point is really probably more like right about there. So it's a better quadratic than what this picture looks like. But, right. So you're gonna both of them seem to be upside down parabolas. Right? So you're gonna fit a quadratic model. So what I have is y hat I equal beta 0, intercept term, plus beta 1 times, I'm just going to call it P for the phosphorus one, plus beta 2 times P squared. All right? So there's my quadratic model for the P variable. Now I want to add the potassium variable, K. I know it starts with a P. Plus beta 3 times K plus beta 4 times K squared. Okay. Now, what about interaction terms? You got all kinds of opportunities for interactions here. You could have P times K times K squared, P squared times K, and so on. But looking at the picture, do you see evidence of an interaction that you should probably try to model? Or can you say, based on the picture, I could probably safely leave those out? What are you looking for interaction?
X or Y.
Okay, you said the intercept would change, and not that, but I know what you mean. The relationship change.
Yeah.
Would the relationship change? And so I'm looking at this line compared to the next line, compared to the next line, and does the shape seem to change dramatically? No. So I don't see an interaction between P and K.
So if you do,
Right.
you have to put like a beta 5.
Yeah, you'd put a beta 5 and then the product of those two variables, right? So, and same thing going the other way. This curve seems to be pretty similar to that curve, just it's higher up. This curve, so I don't see evidence of interaction in this graph. I think some of you, when you answered it, you did put interaction terms in there, and I didn't count off for that, I don't think, but what's that?
There's no interaction of this.
Right. If there is no interaction and you include a term in the model, it just gets a parameter estimate near 0 anyway. It won't be exactly 0, but it'll be near 0, and it'll probably be non-significant, at which point you go, oh, I guess I don't need that one, and you kick it out. Okay, the next page has a correlation matrix, and remember, in this exam, that's when we first learned how to look at correlation matrices. So part of this was just, do you know what you're looking at? Can you interpret a correlation matrix? The first thing it says is, using the above matrix, which variables are good predictors of VO2 max? So if you look at VO2 max correlated with the other variables, you're just looking for ones that are fairly big, and a lot of them are pretty big. 73, 74, 59, it's negative. 83, that one's not big, but that one is. So almost all of them would get circled and say, hey, these are all potentially pretty good predictors. Then a model which uses 4 of the predicted variables is given below. Compute all the blanked out values for that model. All right, so this is what I was saying earlier. I would probably have you fill one of these in for a multiple regression model rather than I definitely won't have you do both. Right. Any questions about how to fill those things in? If you go to the standard error of max heart rate, so I'm looking at this line. To fill all this stuff in, where do you get the standard error of max heart rate?
You go there.
You got to go back to the X prime X inverse matrix. Right? And so you find the max heart rate, you find the diagonal element that goes with it, so that's this number right here, 0.00009812. And then what? You're not done. What do you multiply that by? Okay, you take the square root of the mean squared error times the square root of that thing, and that's the standard error of that max heart rate. And then once you have the standard error, you can get the t-value, the p-value of the test. What about confidence limits? You just find the t critical value, multiply by that standard error you just computed, add and subtract. Right? Now, what critical value would you use? T or Z? It'd be a T. It'd be a T. And how many degrees of freedom?
35.
Not the model degrees of freedom. Error degrees of freedom. It'd be the degrees of freedom for error, so you just look up above, whatever it is, it's 95, what Peyton said. So it'd be 95 degrees of freedom. Okay. That one also had you compute a confidence interval for the mean predicted value, but in order to do so, I had to give you the hat value, or the distance value. Right? So I could give you a hat matrix and have you compute something like that, but the last page is a model with a dummy variable in it. All right, so this was our Da Vinci data. And you had a separate line for males and females. If you look at that plot, does it seem that there's evidence of interaction? And what is it you're looking at? The slopes of the lines are different, so that's evidence of interaction. Later on down, we actually do a test of that, and we find it's not significant, but there is some interaction. It's just not statistically significant. Determine the equations of the lines separately for males and females based on the output. You remember how to do that? You just plug in the value of the dummy variable. It's 0 if it's females, it's 1 if it's males. So you go to your regression equation, which is given in the model here. So you have an intercept term, hand, gender, and hand by gender. So when for females, both of these terms are going to drop out. There's your equation for males. Intercept plus coefficient of hand. When it's... What did I say? That was females or males?
So that
should be female. I said males, but that should be
Male is 1, female.
Oh, males 1. Okay, so for females, these zero out. And then for males, you're going to plug a 1 in for each of those. So you have hand times whatever the length of their hand is, and then plus 1 times this number. Well, that's going to go into the intercept term, right? Because you've now fixed it at 1, it becomes constant. And then 1 times hand is another hand term. So you add those coefficients together to give you the coefficient of hand for males. And here's the test for whether there's significant interaction. It's the product of the two variables tells you whether there's interaction, and the p-value of that test is 0.104. So it's not statistically significant.
Go over D and E. What
Okay, D and E says, D says, do the two lines have significantly different intercepts, and which line of the output is giving you that? So different intercepts. What tells us whether they have different intercepts?
gender by hand. And the third one,
Just gender.
I've heard all answers. It's just gender, right? So gender is the difference in the intercepts. Remember, gender takes on 0, 1, so y hat equal beta 0 plus beta 1 hand, call it h, plus beta 2 gender plus beta 3 gender times h. Right? So if this is a 0, 1 variable, then when it's a 1, this number is beta 2 times 1. It becomes a constant. It is added on here. So it's the change in the intercept. So this coefficient is change in intercept.
So pretty much your dummy variable is the one that tests your intercept.
Right. And then this one tests difference in the slopes. So I asked that same question in two different ways. E says, do the two lines have significantly different slopes? Which line are you looking at? You're looking at the hand by gender. And then F says, is there statistically significant interaction? Well, I just answered that question. But you have to know that different slopes means interaction. Right?
So E is hand by gender. Is significantly different.
Right.
And
Yeah.
how can, I just want to make sure, because you said even at a p-value of 0.1, it wasn't considered statistically significant difference.
Right.
What's the cutoff for that then?
Statistically significant, the cutoff is always whatever you set alpha to be. So it's usually 0.05, so this is not less than 0.05, so it's not statistically significant.
Oh, okay. Sorry, I was.
Now, again, there's a lot of debate out in the statistical literature right now going on about p-values and hypothesis tests, and people are starting to argue you shouldn't even ever do hypothesis tests. It should all be done with confidence intervals. Right? But this is really not that far off from 0.05. Right? So remember what a p-value is. It's a probability. So I have a 5% chance that this is due to random variation. No, now I got a 10% chance it's due to random. That's not that much different, 5%, 10%, right? So I would say, yeah, there does seem to be some evidence, but maybe my sample size is a little too small to pick it up. I don't have enough power for this test. Right?
Because it's above it. That's okay.
Right.
Because normally you say it's consistent. I figured it out.
Okay. Okay, any other questions about exam number 2? Okay, I don't have time probably to work anything on exam number 3, but let me go ahead and pull it up, and I'll just give you some ideas of which ones I think are going to be most important on the final. This is the one where we had logistic regression. I can guarantee you there'll be some logistic regression questions on the test. So make sure you understand how a logistic regression model works and how you get from probabilities to odds and back, and how you get from log odds to odds, and how you get from a difference in log odds to an odds ratio. Right? Remember, difference in logs, when you anti-log, take the exponential of it, then becomes a ratio. Right? So, and that's kind of what this is showing, that when you raise e to the power of a parameter estimate, you get the odds ratio for that parameter. And then we had is this the test where we had the collinearity stuff? Yeah, there it is. So before that, here is a partial F test. Right? Everybody remember how to do a partial F test? You have a full model and a reduced model. And the reduced model, does it have the variables you're interested in it? Or does it?
It does not.
It does not. So the full model has everything, and the reduced model takes out the ones you want to know about, the ones you are testing. It takes them out. So the reduced model doesn't have them in. That way you can see, well, how much did things change when I put those variables in to get to the full model? All right. So that's a partial F test. I can be pretty sure there'll be a partial F test on the final. Studentized residuals and Cook's D and all that stuff. That's probably not as certain that there'd be something like this where you have to go through a big list of stuff, right? But I might just ask, how's Cook's D computed, or what's the cutoff for Cook's D, or for hat value or something like that, without making you sift through a whole bunch of numbers trying to pick out the ones that are big, right? Something like that. Collinearity diagnostics. Expect something.
You would just say what are the cutoff values, not search.
I said maybe.
Okay.
Yeah, if I'm trying to shave time off of it, then that would be one I would cut first, is not having you go through a list of 100 numbers and pick off which one is bigger than 0.25 or something, right? Because that's a lot of tedium. But
You said that you may have calculate Cook's D by hand?
We have a formula for Cook's D that we computed. I don't know if I would do that because it's just a matter of whether you happen to get that one on your cheat sheet or not. But
Oh, sorry, I thought that's what you said. That's why I was asking.
well, I did, but I'm not. As I think about it, I'm not sure. But I would say, yeah, definitely that's a candidate. Right? It's just like computing the standard error of a slope. That if you got that formula on your cheat sheet, you're fine. If not, and you're yeah, you could maybe derive it, but. Okay, collinearity diagnostics.
What's the cutoff for the condition index?
Condition index, the cutoff they gave us in the book was 30. It's fairly arbitrary, but if it gets bigger than 30, then you're supposed to start to worry about it. This one jumps up to 300 for its max. So
And the eigenvalue is 10, right? Or 1.
you mean the variance inflation factor?
The variance inflation, yes.
Yeah, that's a 10. Yeah.
And that's the
We don't really we don't have a cutoff for eigenvalue.
I do.
The condition index is basically the reciprocal, and so we use it instead.
and variance inflation factor. That's the formula's the 1 divided by 1 minus R.
It's 1 over 1 minus r sub j squared.
That's sub j.
And that thing means what?
The R square value at that, for that specific.
Isn't that removed with the G, that observation?
With the jth x variable